Okay. All right, so video's going on now. I've started uploading these in case you forgot. So if you're ever out or if you ever forget what's going on in class, you can go watch these around Schoology now. I think that's all I gotta say. Let me check. Oh, quiz Wednesday, quiz tomorrow, over the first few homework problems. And then what else? Oh, make sure you know the trapezoid formula for tomorrow. I don't think we'll give it to you. Johanna, you won't need a calculator if that's what you're gonna ask.
No.
Okay.
Will we have time to work on this? Yeah.
I think so. Yeah, I think we should. All right, y'all. Here is 6.3. You're in the middle of the year, and only now are you seeing what the foundation of calculus actually is. No, I'm kind of lying about that. This is just called the fundamental theorem of calculus because it combines all the three parts: derivatives, integrals, and then kind of limits are behind the scenes. But that's why they call it the fundamental theorem of calculus. All right. The fundamental theorem of calculus has to do with a function that might be kind of confusing. So we start by introducing that function. You'll see it's not actually that bad. And then we'll get into the actual theorem. Okay. So the function I'm talking about is this function. It's called an accumulation function. Or I like to call it the area so far function. Because what it is, here, let me write that. Area so far. All right, can you read that? Yeah, okay, that's okay. So the area so far function looks like this. It's a function g of x defined from some constant to x. So in this case, the variable is the upper limit of the integral. Okay, so it's the area between a and x, whatever the input is, of some function dt. In other words, it is, if you have some function like this, f, then this function g, the area so far function, would be the area from some starting point, arbitrary starting point a, to x, the input. And this x, this upper guy, is a variable. It can move around. That's what the function is in terms of, as in this can move around, back and forth. And so if it's like from 0 to 1, if x is 1, then you get the area from 0 to 1. If x is 6, then you get the area from 0 to 6, or whatever this number is. If you don't understand that, you'll see in a second. There's an example. Okay, in this case, the input or argument of our function is the limit of integration. Like I said, this function gives us the total change or accumulated change from a to x, or in other words, the area. It accumulates the area from a to x. All right, cool. So still, after all those words, it's very possible that you are confused by this function. But once we do a couple examples, you'll be like, oh, okay, this makes sense. Example 1: the areas of the areas of the regions bounded by the graphs of the function f and the x-axis are given in the figure below. Let the function f be defined by the equation g of x equals this. I think this might have been wanting to be a little g. But I don't know. Either way, we get this function, the area so far function, and then it says evaluate g of 6. Okay, all right. So just like with any other function, g of 6 just means plug 6 into x. So that would be g of 6 is equal to the area from 3 to 6 now, because x is 6, under this graph f of x, or f of t, I guess, because the x is already taken. This variable, this t, doesn't mean anything. It doesn't affect anything. It's just like an x. It's just that we already used x, so we have to do something else. All right, cool. So g of 6 means take the area from 3 to 6 under the graph of f of x. Okay, all right. So here's me doing that. area from 3 to 6 is this guy right here, which the picture told us is 12. That means that G of 6 is just 12. Okay, that's all there is to this one. You see where I'm getting these numbers and why it's 12. So as you can see, it's not as confusing as it looks. All right, G of negative 7, let's do that. G of minus 7 is equal to the area, or the integral, from 3 to negative 7. Negative 7. So f of t dt. Okay, so if I want the integral from 3 to negative 7, this one is weird because, well, we're used to seeing like small number to big number. Now we're getting like the small, like big number to small number. So that's weird. That's not usually what we like to do. We're used to seeing left to right, the integral going from left to right. So we can make it go left to right by using a property from yesterday, which you may or may not remember. You guys remember what happens if I want to switch these so that it looks normal? Nice, 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 nice. Good job, yeah. Okay, so if I want this to look normal, like this, integral from negative 7 to 3. Again, if you don't know what I mean by normal, I mean going from left to right, small to big. Okay, this I know how to take because that looks more normal. But if I switch the bounds of integration, then you got to take the negative. It just makes it negative. This is a property from yesterday. All right, very cool, very cool. And now we can take the area from negative 7 to 3 under this graph. Okay.
What specific property is that, so I can write it down?
This was property 2, the second one.
Why does it matter if it's one way?
It's just, the convention is for it to be defined from left to right. I think that just comes from the definition. Yeah, if you hadn't noticed this, you would have gotten the negative of the answer. But again, that's just because of the definition. Yeah, I'm just trying to think if there's a deep mathematical reason why it matters that we go left to right. But no, I'm convinced that it's just the definition, is just what will make everything work out, what will make all these properties that we learned yesterday like work nicely. So yeah, short answer, just the definition. Yes, Sophia.
Are the areas below the x-axis negative?
Yes, good job remembering that. All right, so let's get this. This would be equal to, let me not forget this negative out of front. This would be equal to negative, and I'm going from negative 7 to 3, right? Yeah. Okay, so that would be equal to negative. Okay, from here to here, it looks like a 10. From here, well, from 4 to 0, it looks like a 15, but like Sophia said, that's under the x-axis. That would be a negative 15. So 10 minus 15, and then minus 9, because that's under. Okay, all right. Then you add all those together, and you get 14. Positive 14. All right, cool. That actually reminds me that yesterday, sorry, let me fix this right now because I didn't notice this till 6th period. Yesterday we did this one with a half circle. And then we got -1 for this area of this triangle. And then I told you pi for this area. But this should have been -pi. I didn't realize till 6th period when a student corrected me. This should be what? -1 minus pi instead of -1 plus pi, which is what you have. Sorry, I forgot that it was under, or like I didn't think about it being under the axis. So again, that's example 5, if you care to fix it. If not, like, you'll probably remember later. Okay, so that's the area so far function, and like I said, that's a big part of the fundamental theorem of calculus, which obviously is an important theorem that we learned in this class. And it shows that there's a relationship between the area so far function and some sort of derivative. So let me show you. On Desmos, I'm going to set this up, but we're going to use Desmos to get an area so far function where the function inside the like graph will be t squared, a parabola, and the function x squared itself. Then we're going to take some derivatives. So let me set this up, and then I'll explain this better. Okay, Desmos. Graphing calculator. Okay, like I said, I want to take g of x to be equal to this stuff, the integral from 0 to x of t squared dt. And I want f of x to be equal to x squared. All right, the graph itself doesn't really matter. Okay, then watch this, you guys, watch this. It wants us to fill out this little table where we plug in specific numbers into f. So like, for example, f of 1, according to Desmos, or according to us, we can just plug the number in ourselves. But 1 squared is 1, so okay, I can fill that out right now. And then let me ask Desmos what not g of 1 is, but it wants me to take the derivative of this area so far function and then plug in 1, which obviously we don't know how to do right now. That's why we're asking Desmos to do it. What is g prime of 1? Oh, it's also 1. Okay, interesting. Also 1. Okay. Now I'm going to do the same thing for the rest of these. F of 2, we know that that's 4, but here's me checking on the computer. Okay, f of 2 is 4, g prime of 2 should be, oh, interesting, it's also 4. 4, 4. Okay, all right, okay. Then it wants 3. F of 3 is obviously 9. Watch this, I'm going to do it with the mouse. 9. And then g prime of 3 is, this just can't be. What? It's also 9? What the heck? All right, let's check 4. F of 4 is 16, obviously, because that's 4 squared. Okay, g prime of 4. What the heck? Also 16. And then you can guess what 5 will be. F of 5 is 20. Well, F of 5 is 25. Is it also 25? What the heck? It's also 25. Whoa, crazy. So what do you think the relationship is between the derivative of this area so far function and f of x?
Same.
Yeah, they're the same. They're the same function. Yeah, I'll just write that. They are the same function. Okay. But with all that computer stuff, it might be weird to see what's actually going on. So let me write it in other words. F of x was x squared, and that's equal to this area so far function. So in other words, x squared is equal to the derivative of this area so far function. T squared dt. I'm just going to say prime up here. That's a prime symbol. Or we could have done d dx at the front.
Does that only apply to x squared, or if it was like t cubed and x cubed, would it also work?
Whoa, interesting question, interesting question. Let's check. So the question was, does that only apply if it's x squared or any function? Oh, sorry, here's what I wrote.
Okay.
This is a prime symbol. Maybe I should have done the DDS because that looks like a 1. That's a prime. Remember, this is the derivative of this is equal to x squared. Okay, all right. So let's check his question because that was sweet. Let's do like, I don't know, x to the 4th plus 7, and then t to the 4th plus 7. Or it's something arbitrary, it doesn't matter. Okay, f of 5 is 632, g prime of 5 is also 632. Whoa, crazy. So it looks like they're the same thing no matter what. And that big discovery is what's called the first part of the fundamental theorem of calculus. So the fundamental theorem of calculus part 1 says that if you integrate something, then take the derivative with respect to the top limit, then you get the function back. In other words, derivatives and integrals undo each other. Whoa! Yeah, you guys thought you were done with derivatives, but there's actually a really, really big connection between derivatives and getting the area under a graph. And it is that they're inverses of each other. So here it is formally, if f is a continuous function on a to b, then the integral function g defined by this area so far stuff is continuous, differentiable, and its derivative is equal to the inside function. So again, one last time, you take the derivative of this, you just get this function back with an x in it. As long as this is just an x up here. Okay, so let me show you some examples. If you get one of these on a test, then these should be like free points because these are so easy. If you're taking the derivative of this area so far function, as long as this is a constant and this is an x, then what you get back is just literally the inside function with an x in it. So that's it, you just smile. Cool. All right, the next example, you have to do a tiny, tiny, tiny bit of thinking. This one, look at how, what's different, well, you tell me what's different with this one compared to the last one.
Backwards, so you just make a negative?
Nice, nice, nice. Okay, good job, you guys. Yeah, the constant's on top, is x is on the bottom. So if you want to switch it so that it matches the fundamental theorem, you can do that as long as you make it negative. So I'm going to show all my work and do the in-between steps, but our final answer will just look like negative this with our x's in it. That's our final answer. But the in-between work, the reason is because that is the same thing as taking the derivative of the negative of us switching the bounds of integration. That's these guys, the numbers. Okay, and then we know that taking the derivative of a negative is the same thing as negative of the derivative, and so on. But anyway, just make it negative, put x's in it, then you're done. Okay, then the last one is the only one that you might have to think a decent amount on. Because now, well, you tell me what's different in this one.
So, x is
Right. This isn't just an x. I'm trying to take the derivative with respect to x, but this right here is a function of x. In other words, we get a function put inside our area so far function. And does that remind you of anything in terms of derivatives, functions? Wow, that was so quick. I was expecting to have to say a lot more. Yes, good job. That should be a chain rule. So when you take this derivative, it'll be a chain rule. As in, it'll be the derivative of the outside function, which will be, according to the fundamental theorem, e to the square root of the input, x cubed, leave the inside alone. That's a 3. times the derivative of the inside, which, do you guys remember? It's been a long time. What's the derivative of x cubed? Beast. And that's your answer.
One.
So I very, very much doubt that on the AP test you'll just get one of the easy ones where this is just an x. But these other two might be fair game, and then that's free points if you care about the AP test. Okay, questions on what I just did and why it's times 3x squared? Nice. Okay, all right. So then, well, we might be close to done, I think. Yeah, I want to stop at part 2. Yeah, we're close to done. You guys can have time to work on homework after this. All right, example 5. The graph of f is shown. Suppose that this g of x is equal to this area so far function. Determine where g is determine where g is increasing and decreasing, and then determine any local. It says local relative. You only have to say one. Local extrema or relative extrema. These mean the same thing. So determine any local extrema on the closed interval -9 to 9. And I asked Mr. Little earlier, he meant only the x values. Because the y values you can't technically get because you weren't given some bit of information. So we only care about the x values. All right, cool. So this one requires a tiny bit of thinking. So think about what we just said. This right here is the graph of f. Okay, but we're asked about g. So what's the relationship between f of x and this weird area so far?
The derivative.
Yeah, really good. F, this function, is the derivative of g. Wait, what? Yes, if you take the derivative of this, remember, all you'll get out is f of x. Okay, all right, okay. So let me write that down. Let me just say this. F of x is equal to g prime of x. If you want to say that in words, you can, but I think this is good enough for most of us. F is the derivative of g. Okay, so we're looking for, you got to keep that straight in your head, and then look for the correct thing. Where is g increasing? Or first of all, what do I look for here? Increasing. Did I hear an answer or no? You guys remember what I look for in terms of the derivative graph to know where it's increasing?
Positive and negative.
Oh, you guys are sweet. Good job. Yeah, that was a long time ago before break, and you still remember. Good job. I care about where this graph that I'm given, again, that's the derivative graph, is above the x-axis. So it looks like I should be increasing where that's above, where it's positive. So that looks like -9 to 4. -9 to 4. And 3 to 9. Oh, yes, good job. Who said that? Good job. -4, sorry. Cool, and then I used square brackets here because it comes to a hard stop and it's included. Cool, all right, and then decreasing where it's under, so -4 to 0 and 0 to 3. Okay, decreasing from -4 to 0, like I said. This time it is rounded brackets for both of these. Because we're not technically strictly below the x-axis at 4 or 0, the -4, 0, or 3. So all of those are rounded. Okay, and then we'll do relative extrema in a second. What's up, Justin?
That one goes for the increasing negative square at like -7.
Oh, I should have. Yeah, you're right. Thank you. Yes. Okay, good job asking that. I should have split it like that. You're right. Okay, so -9 to -7. Union, because that's not technically strictly above, like I said. Union 7 to -7, sorry, to -4. union 3 to 6, union 6 to 9. Sorry. Okay, now we're good. Okay, and then do you guys remember how to find, based on the derivative graph, local maxes and mins?
Where they cross the x-axis.
Nice. Yeah, good job. So that's where they cross, remember, because that would mean that we're changing from positive slopes to negative slopes, which would be a max, or vice versa, negative slopes to positive slopes, which would be a min. Okay, so where do I have a local max? Yeah, only -4 it looks like. Because even though I touch a bunch of times, the only time I cross, like going positive to negative, is right here. So at x equals -4, and like I said, this is the only thing we care about. We can't get the y value right now. And then local min, where do I cross the other way? At x equals, you said 3? Yes, nice. That would be from negative to positive, and nowhere else, because everywhere else I'm just touching but not crossing. X equals 3. All right, good job, you guys. Let me stop this video.